This is the first lesson of Cycle 2 of the Grade 11 Functions course. And as I mentioned before, this idea of cycles that we do in our course in this class is this: I introduce something and we talk about it, and then we move on and we do some other stuff, but then we cycle back and hit the same topics again, do some different things just to keep them fresh in your mind and to keep adding to our knowledge. So we've already learned in the past about domain and range, but mostly what we looked at was from graphs, because graphs are the easiest way to see what domain and range are. Remember, domain is all possible x values as measured on the x-axis. Range is all the possible y values. I think it's probably pretty clear that the easiest way to tell what the domain and range are is just by looking at the graph, right? It's not as easy to tell from an equation necessarily, not always anyway, than it is from looking at a graph or a list of ordered pairs. Often our fallback approach is that we visualize the graph or the type of function to help us look for any possible restrictions, because it's the restrictions that really matter, right? Assuming it's not just a series of points, it's always going to be XER for the domain, but with some restrictions, possibly. And for the range, it's always going to be YER, but again, likely with some restrictions. So if I want to determine the domain and range of a function from the equation, what I would do is I'd look at it and I'd identify what type of function it is. So in example 1, A, it is clearly a linear function. So there's certain things we can do. First of all, try to picture it. Can you picture what 2x minus 3 looks like? Y equals 2x minus 3. It's got a y-intercept of -3, a slope of 2, so it goes up to the right with a rise of 2 for every run of 1. That's going to go on forever. If I can picture the graph and I can think, okay, there's no restriction on the domain. In fact, I could sketch the graph, of course. That's always a possibility. So I could do a quick sketch of the graph. And if it's got a y-intercept of -3 and a slope of 2, it might look like this, right? X, Y, like that. And the domain's going to be all real numbers. I see no restrictions that are necessary on the domain or the range based on the graph. But another way I could think about it is, as far as the domain goes, are there any problems with putting any x values into the equation? So are there any x values that if I put them into the equation are going to cause an error of some kind, a problem of some kind? And if there are, then obviously that's going to require me to do a restriction as well. There aren't. There's no problem. Any number you can think of, positive, negative, decimal, fraction, you name it, rational, irrational, I can multiply it by 2 and subtract 3. There's not going to be any issues with that. As far as the range goes, I can get a y value from no matter what value I put in. It's not quite as easy, as straightforward to get the range as is the domain, because you have to think about what's possibly coming out the other end of the function, so to speak. But, you can do it. And so, yeah, there's no restrictions on this first one. This next one, it's a quadratic, right? I recognize that right away, and I hope you do too. And again, if I can picture the graph, that's easiest. And if I can draw a sketch of it, that's the best, because then I'm back to just getting everything from the graph. So here's a quick sketch. For a quadratic, if it's in vertex form, it's relatively easy. My y value is -1. Sorry, my y value of the vertex, I was thinking. So the vertex is -1, 6. I know I said the y value is -1. That's a mistake. The x value would be -1. The y value would be 6. So I'd have a vertex at -1, 6. Maybe that's up here. And I've got a vertical stretch of -3, a value of -3. So we know that opens downward and it's stretched by 3. The stretch part doesn't even matter. What does matter is it opens downward. So there's a rough sketch of this. Again, there's certain things we can know. In general, all quadratics are going to have domains that are all real numbers. There's no reason to restrict this domain. It can go out to the left and to the right forever. The range is always going to be based on the vertex and the direction of opening. In this case, the vertex is got a highest point, a maximum value of 6 because it opens down. So that means that the range can't go above 6. So it's all real numbers where y is less than or equal to 6 because it does touch that 6. And there's my range for that. Now this one might be a little bit harder for us to visualize. We're not quite as familiar with the square root functions, and it's actually not even in the format that we're really used to. So maybe the first thing I'd do to help me do the domain and range for this one is I'd rearrange it into the more standard format that we're used to. So the x should come first. So I'll just swap places of these two terms. I'll put the negative x first. So all I did was rearrange, put negative x plus 2, that's the same as x minus 2. Then I'm going to actually factor out the negative 1 that's in front of the x, the negative sign. Because that's a k-value, right, a transformation. And if I can think in terms of transformations, I can visualize the graph better. That's why we do transformations. So take out the negative sign, common factor it out, and so when I've got the brackets here, it's minus, and then the inside brackets, x minus 2. Now I'm able to better visualize the graph. The graph will look like this. I know that the parent function for this graph starts at the origin and goes up to the right. That's the parent function. That's y equals square root of x. But this has got a k-value of negative 1, so it's reflected in the y-axis. So it's going to start by going this way, and it's got a d-value of positive 2, because when I pull out the d values, we change the sign, which means it's been shifted 2 units to the right. So if this is 2, then it's like this. So if you ignore the red one, maybe we'll even get rid of it, ignore the red one, ignore the blue one, this is what the graph's going to look like. And now that I can see the graph in my mind, I can do the domain and range pretty easily. The domain has to be all real numbers, as long as they're less than or equal to positive 2. And you can see that as far as the range goes, it's just above anything that's above or equal to the x-axis. So it's all real numbers where y is greater than or equal to 0. Again, I could do this from the equation. I could start thinking what values of x are going to... I can't take the square root of a negative number, right? That's the restricting value on the domain. So what values of x are going to give me positive x values overall? And it turns out that any x, or not positive x values, but positive square roots overall. So when I have any value that's less than 2, once I subtract 2 from it and then change the sign, that'll always give me a positive x value that I can then take the square root of. But it's not so easy to see unless you play around with it. I recommend always putting things think about things in terms of transformation. So put them in the format of a transformation, as I did in this last step right here. Okay. Remember, when functions represent real situations, other logical limitations or restrictions must be considered. So sometimes it's just not enough to go, okay, well, a straight line goes on forever in all directions, so the domain's all real numbers and the range is all real numbers. Maybe if that line is a real-life model, real-life word problem, it might make sense that we're only going to stop at a certain x value or stop at a certain y value because that would fit in with the problem. And that's what this question's about. Ernie and Bert have 24 meters of fencing to enclose a rectangular garden at the back of their house. Express the area of the garden as a function of its width. All right. So you can see on this diagram here that there's only 3 sides of the garden that have to be enclosed. We'll call this shorter side the width and the longer side the length. So if we want to use that 24 meters of fencing, we know that those 2 widths, 1, 2, and the 1 length equals 24. So I can say length plus 2 width because there are two widths, as you saw in the diagram, is equal to the 24 meters of fence. I'm going to isolate L in this case because I want to, well, you'll see where I do that in a second. Let me just do it and then I'll explain in a minute. So if I bring the 2W over to the side, that becomes a negative 2W. I'm going to write the negative 2W first. I always put my variables first when I have an option. That's the same as 24 minus 2W, but I like to have it when I have a variable, I like to have that in there first. The reason I did that is because what I'm being asked to find is the area of the garden, right? So the area, which I know for a rectangle, as we can see this is given as area is equal to length times width. But I just recalculated length in terms of width. In other words, whatever the length is, it's equal to negative 2 times the width plus 24. So I can then substitute that into this function. In fact, I'm going to rearrange length times width could be written as width times length. So I'm just going to rearrange those. And then I'm going to substitute negative 2W plus 24 in for L in this. And then I've got W times negative 2W plus 24. And this is still the same area based on the 24 meters of fencing that I have. It's simply that I've got it down to a single variable. Instead of having length and width, I only have the width to contend with. And I could even expand that out. I could leave it in factored form, or I could expand it out into expanded form. I could just do distributive law where I multiply each term by W, so I'd have negative 2W squared plus 24W. So there's the area of the garden as a function of its width, as I was requested to do in Part A. It didn't say what format to put it in, but I put it in standard form. Now, if I wanted to determine the domain and range of this function, again, there's different things we could do. I could put it into vertex form, but I'd have to complete the square to do that. If you remember how to complete the square, that's great. I'm actually going to review completing the square in a future lesson, so I won't do that in this case. But what else could we do? Well, I could get the zeros based on the factored form here. That would certainly be a possibility. Or I could go to Desmos. Maybe since, Desmos there's nothing wrong with using Desmos, why don't we do that in this case? So I'm just going to, when I go to Desmos, I'm going to replace the A with a Y and the W with X because that's how Desmos works. But otherwise, I'll do the same equation. So Y equals, what was it? I already forgot. Negative 2W. So negative 2 X squared plus 24X. All right, now I'm going to have to adjust my screen so I can see it better. There we go. It's kind of, well, we can see it. I could adjust the axes a little bit, maybe go from negative 5 to positive 10. Didn't go quite far enough. There we go. That's good enough. All right, so we can see it. So there's our parabola, and based on what let's just do the domain and range based on what we see there. So the domain is a parabola. So the domain's all real numbers. I am going to put a restriction on it in a minute, though. So I'll start just without a restriction, though. So D equals XER. And that's where we'd normally stop for a parabola. But think about what this is representing. This is representing the area of a garden versus the width. So on the x-axis is really supposed to be the width that we're choosing, and on the y-axis would represent the area that goes along with a particular width based on having 24 meters of fencing. There's certain things that wouldn't make sense. So it wouldn't make sense, for example, for my domain to go below 0. How could I have a width that was below 0? I can't have a negative width, can I? Also, it wouldn't make sense to go past, well, we can see where I just found the x-intercept of 12. It wouldn't make sense to have a width greater than 12, because then I wouldn't even be able to, if I got to enclose a garden, and I've only got 24 meters of fencing, if I went beyond 12, I wouldn't have enough fencing to enclose it. And even the graph goes below 0, which would, if I could somehow, I'd have some negative area, which again doesn't make sense. So it only makes sense in this case to have the graph be in the positive x's and the positive y's based on these values. So my domain really should go between the two zeros in this case, because that's all that makes sense. So the lower value would be 0, the upper value would be 12, and x, of course, would be in between. Then it could equal 0 or 12, in theory. The range, likewise, we know that from other quadratics that we've done, the range can be, for a quadratic, can be anything less than the vertex. So the vertex, the maximum value occurs at 72. So in the past, we just say that y has to be less than 72. So y is less than or equal to 72. But again, in this case, it doesn't make sense to go below the x-axis. Then we'd be getting into negative area. Remember, the vertical axis is measuring area, so how could I have a negative area? So again, I've got a restriction on the range as well. So I can't go below 0. And actually, I shouldn't be using x and... This switches. I used x and y on the graph because that's what Desmos does, but let's use it in terms of what's going on here. So the domain was the width. So the width could be any real number, but it has to be between 0 and 12. And the range, of course, is the area. So A could be any area between 0 and, what was it, 72, I think? Or is it 72, yeah. Between 0 and 72. And when I use those variables, it's easier to remember that they're representing width and area, and to help us understand why it can't go below 0 for either width or area, and why there's a maximum as well. So, just to sum up, when we're doing domain and range with equations, if at all possible, look at the graph. If you're just doing homework, you could always type it into Desmos and see what it looks like, but you also need to consider